Good afternoon. So today we're going to go over yet one more application of the Riemann integral, namely the computation of the surface area of revolution. So let's go over briefly what we did in terms of applications so far, or at least the geometrical applications. So we learned how to compute the area between curves, then we learned how to compute volumes of revolution. So make sure you don't confuse today's lesson with the volume of revolution. So in that case, we rotated a region in the plane, maybe bounded by a couple of functions, the graphs of a couple of functions. So you rotated that surface, which basically generated a volume of revolution. In this case, what we're going to rotate is a curve about an axis, and that will generate a surface of revolution. So basically the goal here is to find the area of that surface as opposed to the volume in the previous applications. Oh, we also figure out how to find the length of the curve, right? The arc length in the previous lesson. So let's go over the main idea about the formula a little bit faster than before so that we can focus on the a couple of applications. I want to point out that this is very related to the arc length that we learned before. So if we imagine, so take a moment to sketch this graph. So suppose this is the graph of a function, which let's assume that you can write it either as a function of x, y equals f of x, or as a function of y if you're able to solve for x and write it as a function of y. And let's say we're going to rotate this about the y-axis, about the x-axis. If you do that, then the surface area looks like this, roughly speaking. So just like before, like with all applications of Riemann integral, to come up with the surface area, you want to produce a Riemann sum by partitioning the interval AB, the domain of the function, but with the difference that each piece of the Riemann sum will give you a small piece of the surface area, or whatever you try to compute, in this case the surface area. So if you imagine that each of these strip corresponds to a small partition of segment on the partition on the domain AB, the goal, if I take that strip out, is to compute its surface area. So this is essentially like a thin band or circular band. If you view it from this direction, for example, it should look essentially like a circle, but it's in reality is like a cylinder, right? And with the important distinction that this piece on the curve itself that corresponds to dx is going to be a piece of the arc length, for which we remember we have a formula from the previous lesson. By the way, there is a notation for the arc length which I forgot to mention last time. So in general, if you have a curve, the corresponding piece on the arc length that corresponds to a small change in x is typically denoted by ds in calculus. So ds is the length of a small arc of the curve, small piece of the curve, the length of it. And if I take this strip that I have to compute its area, and imagine you cut it and then lay it down on the plane like that, this is nearly like a rectangle, with the exception that the sides are given by ds, the length of the curve, the piece of the curve corresponding to dx, and the length of the strip will be actually the circumference of the circle, right? Because it came from cutting this along the side and then laying down on the plane, which means this side here is going to be 2 pi times the radius of that circle. We're going to get to what the radius is once we get back to the function itself. But this is where the formula comes. So therefore, the area of the strip is going to be 2 pi times the radius times ds, which is the arc length. And the surface area for the full surface of revolution, let's denote it by SA, is going to be the 2 pi. We can pull the 2 pi out of the integral. The integral with the appropriate bounds, we'll get to that in a minute, radius times ds. ds is going to be again given by square root of 1 plus f prime squared, which we remember that came from the arc length, the previous lesson. But that is the generic formula for the surface area of revolution. We're going to make another figure immediately to write down actually what this means in terms of f of x or g of y, depending on whether you want to integrate with respect to x or with respect to y. So once again, the generic formula is essentially to integrate over surface area of these little strips that came from the partition. And the area of each strip is the arc length for that small piece times the radius of that circular strip. And with the 2 pi outside, right? So 2 pi times the radius, remember, that's the length of the circle, or the circumference of the circle. Okay, so for an actual function, so let me actually do it again here. So for an actual function between a and b, or between c and d, if you view it as a function of y, what does that mean, the radius and ds? So let's say you want to use integration with respect to x, and again the axis of rotation, let's say, is the x-axis. Well, just like before, you take a generic variable in the domain between a and b. So that basically identifies one of those strips, and therefore the surface area will be 2 pi the integral from a to b. The radius will be f of x. So keep in mind the radius will be the y coordinate of the point on the graph. But if you want to integrate with respect to x, that y coordinate is f of x. ds, the length of the curve, using the same variable, remember from the previous section, it's 1 plus f prime of x squared. And there it is, that's the formula for the surface area. So you see it's very related to the arc length. If you have just this radical, that'll give you the arc length, and without the 2 pi, of course. Together, the arc length combined with the radius and 2 pi, this product will give you the surface area of revolution. And you have to remember, because that's important, that you can actually write the same formula in terms of x or y, because sometimes you may have a preference. We'll get to that. We're going to go over an example both ways, but it's important to know that you're not confined for this case, when you compute the area of revolution, you're not confined to a variable of integration. You can switch it to another variable if you so desire. So for example, the same formula in terms of y, let's say I'm writing x as a function of y instead of y as a function of f of x. Then obviously in that case, the integral will be with respect to c and d, the domain for y. So it's going to be 2 pi the integral from c to d. But because the axis of rotation, pay attention here, because the axis of rotation is still the x-axis, the radius is still the y-coordinate. And how do you write the y-coordinate in terms of y? Well, that's just going to be y. And the arc length will be 1 plus g prime of y squared dy. Many people sometimes are confused on when they ask themselves, do I write the function or do I write the variable? And remember, the answer is it depends. Sometimes people get frustrated with me when I teach it in a live classroom, because I never tell them the answer, is a y, is g of y, is f of x, is x, because any of these four possibilities is possible. It can be y, it can be x, it can be g of y, it can be f of x. It depends on two things: axis of rotation and whether you want to integrate with respect to x or y. And just take a look at this, the other two versions. Let's say you have precisely the same function, but now you decide to rotate it about the y-axis. So if I rotate it about the y-axis, then the surface of revolution is going to be like that. So here's the bottom circle if you want. A typical strip radius will be this from the point on the graph. And so notice that the radius now will be the x coordinate of that point on the graph. And the formula is the same, radius times ds. And again, you can write it in terms of both x and y. So how do I write the surface area in this case in terms of x? Well, it's going to be 2 pi. The domain for x is still a and b. But now the radius for the strip is going to be x. What is the x coordinate of a point in terms of x? That's just x. And then continue with 1 plus f prime of x squared dx. And then finally, if you decide to integrate with respect to y, then the surface area is going to be the integral from c to d. Now I want to get the x coordinate in terms of y, so I have to view this as a function of y, right? So x in terms of y is going to be the function in terms of y, and then square root of 1 plus g prime of y squared dy. So you see there are actually 4 versions of this. That's why it's far better to just remember the generic formula, 2 pi radius times ds, and then adapt it to whether you want with respect to x or y, and then whether you have the x or the y axis as the axis of rotation. So with that in mind, let's move on to examples on the next page. All right, so let's take a look at this example. Y is square root of 5 minus x, and x is between 3 and 5. And the corresponding y coordinates are 0 and root 2 for these points, right? So the domain for y is going to be 0 square root of 2, right? If you plug in 3, you get square root of 2 for that point on the left. And let's say the curve is rotated about the about the x-axis, and we want the surface area of revolution. And let's do this in terms of both x and y. You have to do it only one way. I mean, you don't have to do it twice, but for now, just to make the point as an exercise, let's do it both ways. So the surface area, let's do it in terms of x. It's going to be 2 pi, the integral from 3 to 5. Take a typical x on between 3 and 5, and the radius is going to be the y coordinate in terms of x. So that's going to be the function itself, square root of 5 minus x. And then under the radical, we have to pay attention to the computation here. We're going to do 1 plus the derivative of y to the power 2. So maybe let's write the derivative of y, which is 1/2 5 minus x to the minus 1/2 times minus 1. Let's pay attention to that chain rule. So you differentiate the power and then the 5 minus x on the inside. If you want to write it as a radical, that's going to be minus 1 over 2 square root of 5 minus x. Go slow when you have these negatives so that you don't mess up the computation. So inside the radical, we have 1 plus the derivative to the power 2. So this derivative that we just found raised to the power 2. Obviously, we have to do some algebra here so we can integrate it. This is actually, you'll see, it's actually easier than it looks if you are patient with the algebra. So it's going to be 1 plus, let's raise this to the power 2, which is going to simplify the radical. So it's going to be 1 for quantity 5 minus x. One more, we're going to have the common denominator, 4 times 5 minus x, and on the top is going to be 4 times 5 minus x plus 1. And let's distribute this big radical to the numerator. Let's expand that inside, so it's going to be 20 minus 4x plus 1. And now if you take the radical on the bottom, that's going to be 2 square root of 5 minus x dx. And so notice that the square root of 5 minus x cancels. And 1 over 2 with 2 from the outside. And now we have the integral of square root of 21 minus 4x. Make sure you don't give up easily when you see stuff that is ugly, like a radical. Because you guys went through the troubles of integrating some radicals that required trigonometric substitutions, but remember that was when you had x squared under the radical. This guy actually is just a u substitution, because if you take u to be the inside of the radical, du is just a constant times dx, which is essentially a very basic substitution, right? You just have to go patiently so that you don't make a mistake with the bounds. So take u to be the quantity under the radical. Du is minus 4 dx. When x is 3, u is 21 minus 4 times 3. 21 minus 12, that gives me 9. And then when x equals 5, u is 21 minus 4 times 5, that's going to be 1. So, and then of course, remember du, you got to move over minus 4, because you're going to replace dx with minus 4. So now the new bounds, the lower bound is 9, the upper bound is 1. This becomes square root of u, d over minus 4, minus pi over 4, write u as a power, and then finally do the last integral. Let's see, u to the 1/2 plus 1, that's 3 over 2. We have 2 over 3 in front of it, and then 9 and 1. All right, so let's see, this becomes minus pi over 6, right? So it's going to be minus pi over 6 times 1, and then minus pi over 6 times 9 to the 3/2. All right, so if I pull pi over 6, that's minus 1 plus 27. That's like square root of 9 to the power 3. So 26 pi over 6, which simplifies to 13 pi over 3. Some problems in the homework, 1 or 2, cannot be solved by classical means, and the problem mentions, and in that case just make sure you set it up correctly and then you use a computer algebra system to actually solve the integral. I'm going to actually ask you to do just that with another example a little bit later today in this lecture. But I want to go back to the formula and emphasize that most of the time you do have a choice whether you integrate with respect to x or y. And sometimes you may care about the choice, because when you set the integral one way, it's easy to solve. If you choose, and if you have it in a different variable, it might not be easy to solve. This one can be solved both ways, and you decide which one you would prefer, like which one is easier, if anything, if there is any difference to your liking. So let's say I want a function in terms of y. So you take the original function and you write it in terms of y. And this can be easily done if the function is 1-to-1 over this domain, like it happens here. So square both sides of the original function and get x by itself. So x equals 5 minus y squared. That's the same function, but as x a function of y. And don't forget that, of course, now the domain for y is 0 square root of 2. Everything else is the same. So the curve is rotated about the x-axis. Nothing changes. But now the surface area is going to be 2 pi, the integral from 0 to square root of 2 now. And then the radius, it's still the y-coordinate. Look at the picture here. The radius, because the radius is because what the axis of rotation is, right? So the axis of rotation decides which segment, horizontal or vertical, gets to be the radius. Radius is still the same because the axis of rotation is still the same. But now the radius is supposed to be written in terms of y. So if you have a function of y like that, how do you write the y-coordinate in terms of y? Well, the clue is in the title, right? So just y. Y is the y-coordinate in terms of y, obviously. And then you continue with the rest of the formula in terms of y. So it's going to be 1 plus the derivative of the function itself, g of y, to the power 2. So dx dy, let's do it separately here. That's going to be minus 2y. So inside the formula here, you're going to plug in the derivative to the power 2. And then that's the integral. So if I do it correctly, this should give me precisely the same answer because it's the same surface area. Now notice this also is suitable for a substitution. Pause for a moment and see if you can figure it out. You should always pause the video and try to finish the example ahead of me, and then check with me later, just for practice. So the substitution is 1 plus 4y squared, which works because you have y outside and du is 8y dy. The new bounds are, let's see, when y equals 0, u would be 1 plus 4 times 0, so that's going to be 1. And when y equals square root of 2, u equals 1 plus 4 times root 2 to the power 2. That makes it 4 times 2, 8 plus 1, 9. Okay, so then the new integral becomes 2 pi, lower bound is 1, upper bound is 9. Let's see, the radical becomes square root of u, or u to the 1/2. Y dy from the substitution, remember 8 must be on the left side. It's going to be 1 over 8 du. Pull the 1 over 8 outside and then integrate 2/3 u to the 3/2 between 1 and 9. 2 to 4 over 8, that makes it pi over 6. 9 to the 3/2 minus pi over 6, 1 to the 3/2. So that's 27 minus 1. Obviously, it's as expected, 13 pi over 3. All right, so in the last, we're going to have a quick extra example. In fact, I'm going to actually do the same example, but change the axis of rotation. Those integrals actually are going to be harder to compute. Well, not overly hard, but you could also use in that case the a computer algebra system. So stay tuned for the last example. All right, so let's take a look at the same example, but this time the axis of rotation is about the y-axis. So then this will be the radius. Whether you express it in terms of x or y, that's going to be the quantity you want to put in the integral. And again, like I said before, you have two options with respect to x or with respect to y. Let's say you want to integrate with respect to x, then the surface area would be 2 pi, the integral from 3 to 5. Well, the x-coordinate, the radius happens to be the x-coordinate of this point. X-coordinate in terms of x is just x. And then you're going to have, so remember dy dx, we did that before actually. That's going to be minus 1 over 2 square root of 5 minus x. So for the ds, for the arc length, you're going to have here 1 plus 1 over 4 quantities 5 minus x if you square this radical. This is going to be hard to compute. Use the computer algebra system. This should be approximately equal to 66.5. I mean, I don't even know if actually it's possible to compute by classical means. I mean, but anyway, it's not an easy integral. You don't have that nice cancellation of square root of 5 minus x like in the previous case. If you decide to do it with respect to y, again the same surface area, then of course now the domain is, the bounds are 0 and root 2. The x coordinate in terms of y will be 5 minus y squared, and then the arc length will be, so remember dx dy was minus 2y, the arc length was 1 plus minus 2y squared dy. This is also very hard to compute, or impossible actually, but plug it into a computer algebra system or like something like Wolfram Alpha and see if you get this answer. So I want to finish here today's lesson with a hint for one of the homework problems. In one of the homework problems, you'll have, and actually, I'm going to figure out actually how many people in fact watch these videos carefully, because I can tell if they don't know the hint. So hint for the homework problem. And in that homework, one of the functions involved there is y equals 1/3 x to the power 3 over 2, with x between 0 and 12. And if you set up correctly the integral, you should end up at some point to to the surface area being equal to the 2 pi, the integral from 0 to 12 x square root of 1 plus x over 4 dx. Okay, so there's no obvious way how to do this because there is no obvious technique of integration that you can use. So occasionally I throw these problems in because these techniques of integration work for some specific cases that are obvious, right? So for example, like you saw in the previous page, a u substitution worked clearly because you had the du accounted for and so on. But in some other cases, it might be just worth trying a technique just to see if you get something doable. It's not like the technique would work from the beginning, but it might bring you the problem into a form that you can actually solve by using a different technique maybe. So this is a moment of kind of guessworking to an extent. To an extent because, for example, so here's the hint. Take the substitution u to be 1 plus x over 4. It's not obvious if this works in the beginning because you may say, well, I still have an x on the outside and your du is just 1 over 4 dx. And that is true, but if you look carefully, via this substitution, we might get actually in the end a combinations of powers of the new variable, because when you solve for x you get a polynomial, a linear term in terms of x, in terms of u, and combined multiply by square root of u, then you could see that basically this leads to a combination of powers of u, and then it'll be just the power rule. But to be clear, let's actually follow a little bit these steps before I leave it to your own devices. So don't forget to change the bounds like we normally do for any substitution. So if x is 0, u is 1 plus 0 over 4, which is 1. If x is equal to 12, u equals 1 plus 12 over 4, which is 3 plus 1, and that's equal to 4. And remember, in the actual integral, we're going to have to replace x as well. And we get that from the substitution here. So move the 1 over, and then get x as 4u minus 4, right? If you multiply u minus 1 by 4. So the new integral then becomes 2 pi, the integral from 1 to 4 now. X is going to be 4u minus 4. And then the radical becomes obviously square root of u. And then dx is 1 over 4 du. So in fact, I should have kept this 4 on the outside. So you can pull out 2 pi you can pull out 4 out of these, and then 1 over 4 from here. And that's just going to be 2 pi integral to 1 from 1 to 4. And then if you distribute now square root of u times square root of u as a power, well, let's do it one more step here so you can clearly see. So you replace square root of u as a power, and 1 plus 1/2 is 3 over 2 minus u to the 1/2. So it becomes just the power rule, and you can finish it up from here. So with that, that's it for today, and I'll see you next time.